Good day everyone, my name is James Lowell Laran. Into this video, I'm going to explain or discuss the pattern and diagram Rosette and Frieze pattern. So, Frieze pattern. An infinite strip with a repeating pattern is called a frieze pattern, or sometimes a border pattern or an infinite strip pattern. The term frieze is from architecture, where a frieze refers to a decorative carving or pattern that runs horizontally just below a roof line or ceiling. Some examples of frieze patterns is, so as you can see, the pattern repeat. We show only a finite portion, but in the picture, it extends infinite far in both directions. So although most of the frieze pattern in this example will be horizontal, there's no reason a frieze pattern cannot be a vertical or even a angle. So it says that all frieze pattern is a horizontal. There is no vertical or angle that shows in frieze pattern. So translation symmetry. All frieze patterns have a translation symmetry. A horizontal frieze pattern looks the same when slid to the left or right. A vertical frieze pattern looks the same when slid up or down. And in general, any frieze pattern looks the same when slid along the line it is laid out upon. Again, it is important that the pattern extend infinitely far in both directions, so that there are no ends that appear different. So it says that all the pattern or all the arrow have no end appear. So there is no end in the kind of any example like this. So as you can see, a short arrow describes a translation, but generates all the longer translation. Also, the longer arrow may also give translation symmetry because it multiplied times the shorter translation. We will only label the shortest translation in a given direction. So another example, clearly if a strip has a translation symmetry to the left, then there is to the right. So we can say that if there is a left, there is a right. So it reverse the arrow describe the translation symmetry. So the reverse arrow provide no extra information, so we will not label. In summary, displaying one minimum length arrow indicates an entire family of translation symmetries, all of which point in one direction or its reverse. We say that this collection of symmetries is an direction of translation symmetry. So if the arrow was going to the left, it is called a direction of translation symmetry. We can give a more. So frieze pattern can have other symmetries as well. For example, the figure below has infinite many reflection symmetries as well as a horizontal translation symmetry, both marked in red. So it has a translation symmetry common to all frieze patterns. However, the symmetry between the left footprint. Practice looking for symmetry in frieze pattern with the frieze marketing exploration before exploration. So this is one example of horizontal translation symmetry. Next, glide deflection symmetry. So in this pattern, below is a kind of symmetry. It figures we label a glide deflection symmetry with a dash arrow. The length of the arrow shows the translation length and direction, and the body of the arrow lies on the axis of reflection. In the figure below, the translation symmetry is also shown as a solid arrow. So it has the translation symmetry common to all Frieze pattern. The symmetry between the left footprint and the right footprint does not come from translation, nor is it due to a reflection, since the prints are not next to each other. Instead, the combination of translation and the reflection is needed. This combination is called, so this example is called a glide deflection symmetry. So glide deflection symmetry can be hard to spot. Keep an eye out for zigzag or wave line, as these often have glide deflection symmetry down their centers. So classification of Frieze symmetry groups. So Frieze group are symmetry group of Frieze pattern. They have only one direction translation symmetry. In this section, we assume that strip returned, so its translation is horizontally. Frieze group exploration. Before continuing, the first observation is that Frieze pattern cannot contain only a very limited selection of symmetries beside a single direction of translation symmetry. So Frieze group exploration or Frieze group is, there are many naming systems for Frieze group besides the IUC notation. Learn some Frieze names exploration. We use the names of the symmetry groups that were standardized by the International Union of Crystallography or IUC notation. These names are begun with P followed by 3 characters. A horizontal 3 characters. The first is M if there is a vertical mirror, horizontal reflection. 1 if not. The second is M if there is a horizontal mirror or vertical reflection. A if there is a glide deflection and otherwise 1. So the third is 2 if there is a 180 degrees rotation and 1 is not. So this is some example of 7 Frieze group or Frieze group. So this is, so P11 has only the translational symmetry. P1M1 has a horizontal mirror symmetry. PM11 has vertical mirror symmetry, space half the translation length. So PMM2 has vertical mirror symmetry, horizontal mirror symmetry, and 180 degrees rotation where the mirror intersect. P112 has only 180 degrees rotation space at half the translation distance. P1A1 has a glide deflection, half the length of the translation. And PMA2 has a glide deflection with alternative vertical mirror and 180 degrees rotation. So some example is this. This pattern is a ceramic design. So ceramic design, the translation symmetry of this pattern is vertical. The only additional symmetry of the pattern is a reflection axis, which is along the direction of translation. This pattern has symmetry group of P1M1. Another example is the strip on the right is a tile pattern. So all the triangle the pattern, the horizontal and vertical reflection axis is marked and ordered 2 rotation centers. Wherever there are axes crossed, it has a symmetry group of PMM2. So in the third example, so all the triangular arrow shape point to the left. This pattern has no vertical reflection symmetry, as it will reverse the arrow shape to point to the right, the same reasoning show. So all the triangle showed was going to the right, it's called a, or point to the right has no vertical reflection symmetry. So the picture below shows a portion of pavement. Notice the figure has no reflection symmetry. To be sure of this, we look for a detail in the figure whose mirror image does not appear. For example, part of the red Mender line looks like the letter S, since the mirror image of the S does not appear anywhere in the pattern. The pattern has no reflection symmetry, not even blind reflection symmetry. So, in the example, we say that S details with the rotation center, but the second picture, we see that it repeat, or say it's a Frieze pattern that which called this a Gaia was Gisundo of the second picture. So the order of two rotation center at the center of the S details is also a rotation symmetry of the entire strip pattern. Knowing that the rotation center must be spaced at half the translation length helps to spot the other order two rotation symmetries as shown in the marked image below. This example shows the symmetric group of this Greek K pattern is P112. So Rosette pattern can observe when viewing a printed piece with a loop. Or magnifying glass, and from a certain perspective almost resembles a multicolored bouquet of roses. There are two common types of Rosette pattern, the dot-centered and clear-centered. Dot-centered. As the name implies, the dot-centered rosette can be identified by the dot. So, it says that visible in the middle of the rose pattern. All you can see in the example is all that can form a rose pattern. So this type of rosette tends to show a less visible pattern at the cost of a slight loss in gamut and shadow details. It is also more susceptible to color shift due to misregistration. This pattern is typically used for lower quality jobs of 100 LPI and lower. Thus, the clear centered or open centered, which are created by shifting one of the process color. One half row of dots from the other colors. Also, this rosette results in a slightly more visible pattern. It tends to preserve shadow details under cease color shifting. This pattern is better suited for higher quality jobs, or 150 LPI and higher. A rosette pattern is a pattern that has either of the following types of symmetry: cyclic symmetry, rotation symmetry around the center point but no mirror lines. So it has a rotation but have no mirror lines. So it is if there is no mirror line and have a rotation symmetry, it's called a cyclic symmetry. So the dihedral symmetry, rotation symmetry around the center point with a mirror line through the center point. Next is orbifold rotation rosette. In geometrical orbifold rotation is a system invented by mathematician William Thurston and promoted by John Conway for representing types of symmetry groups in two-dimensional space constants curvature. The advantage of the notation is that it describes this group in a way of which indicates many of groups' properties. Group representable in this notation includes the point group on the sphere, the Frieze group and wallpaper group of the Euclidean plane, and their analogs on the hyperbolic plane. So this is the example of orbifold notation for abigams. An abigam is a word or design that retains meaning when viewed for an ambigram is a word or design that retains meaning when viewed from a different direction or perspective. Especially a rotational ambigrams read the same when viewed upside down, while a mirror or bilateral ambigrams is one that reads the same backward and forward. This is the example of ambigrams. As you can see in the picture, it is the calligraphy design that has a several interpretation written. We always use this in school or since elementary. We use a calligraphy or a ambigrams in other subject. So fundamental domains. A fundamental domains of a symmetric set is a subset that contains at least one representative from each of the symmetric equivalence classes or orbits in the set. This paper contributes a novel polynomial algorithm for constructing minimal polytopic fundamental domains of polytopic sets. Our algorithm is applicable for generic linear symmetries of the set and has a linear complex in the number of phase set and dimensional of the symmetric polytope, the feasible region of an optimizing problem. So, the algorithm are demonstrated in 4 examples, 2 illustrative and 2 practical. In the first practical example, we show that a minimal fundamental domains of the hypercube under the symmetric group in the set of points with sorted elements. In the second practical example, we show how the construction algorithm can be applied to the max cut problems. So this is the example of fundamental domain. The tetrahedron, the cube, the octahedron, the dodecahedron, the icosahedron, triangular, square, pentagon, hexagon. So, paper cuts. Paper cut outs. As a child, you may have made snowflakes pattern by folding a piece of paper and cutting along the edge. Make a snowflakes representing as many of these symmetry groups as you can, D2, D3, D4, D5, D6, and D8. Devise a way to make a snowflakes with a Cn symmetry for any values of n that you choose. So paper cut is a centuries-old techniques that was initially practiced by a Chinese artisan. So this is an example of paper cut. So it says that in the picture, we know that paper cuts is a technique of a Chinese artisan, but we can do this also since we are a children at a grade school. So that's all. Thank you for watching the video, and I hope you learned something in my video. Thank you and goodbye.